Hello and welcome. So today we are going to start talking about the new chapter, chapter 23, and we are going to introduce a new concept, which is called electric potential. It is kind of like the potential energy we discussed in the first semester, but it's a little bit different. And these are the reading assignments, and these are the suggested problems. I think I'll be able to go as far as half of this material today, and we can probably finish it next week. Right? So first, let's introduce electric potential energy. And for this, we can start from defining the work, right? So to be more concrete, we can think of like a scheme like this, but for now, let's keep it general. So work is defined as usual. I'm assuming a constant force, as in this example, so I don't have to deal with integrals. It's like simple f dot d, or you can do it like f dot dx, and if you take the integral from 0 to d, you're going to get f dot d for a constant force. So you remember the electric field of a parallel plate. One is like plus charge, the other one is negative charge. And I think, talk about this extensively. The electric field was unidirectional. It was like only along x direction. And we ignored these like edge effects. And the magnitude of the electric field was also constant. So electric field here was same as electric field here, was same as electric field here. Okay. Then we can write an expression for F here. And if you have like a charge Q starting from here, the force it experiences is Q times E. Then the work is Q times E times D. Now we can go back to first semester and remember work energy theorem, which says work done on a system, negative of the work done on a system with conservative forces is equal to change in potential energy, right? Something like that. We define like a potential energy of this charge, and it is the potential energy at point B minus potential energy at point A. And this difference should be equal to negative of the work done on the system by this conservative force. But we already calculated W, then this potential energy difference is minus Q times E times D for this simple example. Okay, this is electric potential energy for a charge in constant electric field. Now I want to introduce something called electric potential. So the problem with this kind of expression is like there's a charge here, right? And we don't want to deal with these like charges, and we don't want to put, so we want to be able to determine an electric field and its potential by just looking at the field. So to eliminate the charge, we introduce something called electric potential, and it is defined as electric potential energy per unit charge, right? Similar to electric field. So electric field was force, electric force acting on a unit charge, and electric potential is the electric potential energy per unit charge. So we can write it like this. So we generally use V for electric potential, and its definition is like something like this. Okay, here V is electric potential, U of A is electric potential energy, and Q is charge. So you can work out the units. So energy unit is joules, right? Or Newton meter. or kilogram meter per second squared times meter, which is joule. And if you divide it by Coulomb, you have the unit of electric potential. And we generally call it volt. Okay? So 1 volt is equal to 1 joule per Coulomb. So generally, when we are talking about potential differences, or maybe sometimes potential energy differences, we are measuring something with a voltmeter, and we call it the voltage. That's what it is. So if you remember from the first semester, the potential energy was only defined with respect to a reference point. So the only important or the only physically meaningful object was potential energy differences. Since electric potential is defined in terms of electric potential energy, this same concept carries on. So we can only talk about potential differences, electric potential differences to make perfect physical sense. So when we say this, it's kind of like VAB, that's like an electric potential difference between B and A. It's defined as VB minus VA. Or if you split this up, like here, this is like UB over Q minus UA over Q. And this is like work done for carrying a particle from B to A divided by Q. And there's like an overall minus sign, which is the definition of potential energy. Okay. So the nice thing about this, if you have the electric potential, you can get the electric potential energy. You just multiply it with Q, right? Q times V is going to give you U. But for this, you have to be careful because Q can be positive and negative. And if like Q multiplying this is negative, that means negative charge has like a high potential energy when the potential is low, okay? Or positive charge, for the positive charge is the opposite. So that means negative charges move towards the high electric potential, positive charges move towards the low electric potential. Like this is another way of saying, if you have like a positive charge, it's going to move towards low potential. So this is high potential, this is low potential, and positive charge move like this. Whereas negative charge, this is again low potential, this is high potential. Negative charge will move like this because it moves from minus to plus. All right? So another thing to be careful is like potential energy also depends on the charge. So it's actually similar to what we know, right? If you have a small rock and a big rock at the same height, so big rock has the bigger potential energy because it has the bigger mass. So the same thing applies here. If you have like a bigger charge, even though the potential is the same, or potential difference is the same, bigger charge has the bigger potential energy because of the charge. Exactly like this. Okay. I don't understand why plus side is high potential energy and minus side is low potential energy. So it's from this, right? We just calculated this. We said work done on a charge Q is equal to F dot D. I spelled out charge Q times E times D. And I defined the potential energy difference between here and here as minus the work done. And it was like minus QED. And the potential was defined as the potential energy difference divided by charge. So from this, we got, this is like the high potential, this is the low potential. So you can think of this like this, right? So if you have like a positive charge, this is kind of like acting gravity, right? Like I think maybe I can write it like this. So you can think of this parallel plate. So this is plus, 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 this is minus, minus, minus. And if you have a charge, it's going to get like an electric force, or there will be a corresponding force E times or Q times E, and it's going to be exactly like this gravity, right? So for the gravitational case, this higher ground has the higher potential energy. This one has the lower potential energy. And for this guy, it has to have high potential energy here, low potential energy here for positive charge. And if we eliminate the charge by defining this, this is the high potential, this is the low potential. So let's get a sense of these potential by looking at some values. What is the potential differences of certain things we see around? I think if you look at a thundercloud, I think typically its like value is 10 to the 8 volt, right? Like thundercloud to the ground is like about 10 to the 8 volt. But it is like what? So 10 to the 6 is about 1 million. 10 to the 8, 100 million volt, right? A gigantic number. So if you ever walk by high voltage power lines, you probably hear their noise from like hundreds of meters, right? And if you look at their voltage, it's like 10 to the 5 to 10 to the 6, 100,000 volt or 10,000 volt. So the power supply for a TV tube, I guess this is like old TVs. I don't think this is like for LEDs that we use today. It's about 1,000, maybe 10,000 volt. Like an auto ignition is like, again, the same order. Your household outlet is like, I think it's like 120 volts in Europe. I think it's around like, or like, what is it? I don't remember. I think in the US, it's like half of that. 120 in US. What about in Europe and Turkey? 240, right? Yes, that's around that like. So flashlight battery, 1.5 volt, right? And resting potential across nerve membrane, that's like something biologists tell us, it's like 0.1 volt. Even there's like a measurable voltage difference. And the potential changes on the skin, I think the hospitals have this, they can, I guess, measure this. EKG or EEG is 10 to minus 4 volt, which is very tiny, but still measurable. All right, let's solve an example and try to see. Suppose an electron in a cathode dye tube is accelerated from rest through a potential difference. VB minus VA is equal to 5,000 volts. From here to here, 5,000 volts. And the question is, what is the change in electric potential energy of the electron? And B, what is the speed of electron as a result of this acceleration? So let's start. So A, okay, we are asked about the change in electric potential energy. So it is like what? UBA is equal to charge times VBA, and charge is minus the electron charge times VBA. And if I put the numbers, what is the electron charge? Something like 1 minus 602 times 10 to the minus 19 Coulomb. And this is times VBA. This is like 5,000 volts, which is joule per Coulomb. But joule is equal to what? Oops. Joule is equal to Newton meter, which is kilogram meter per second square. This is Newton times meter, right? This is kilogram. So I think, I mean, this thing is joules, so we have the energy as V should. So we can multiply these numbers. What is that? Which is equal to minus 8.01 times 10 to the what? Minus 16 joules. So B, what is the speed of the electron as a result of this acceleration, right? So we know delta K plus delta U should be equal to 0 because it's a conservative field. Then change in kinetic energy is equal to minus change in potential energy, which is equal to what? This side is 1/2 V squared. This side is this guy. So from this, we can get V is equal to something like 2 minus 2 delta U divided by M. And if we put the numbers, what does it give us? Like, okay, maybe I can do this. 2 times 8.01 times 10 to the minus 16. Okay, let's write the units to be sure. This is kilogram meter squared per second squared. Divide this whole thing with kilogram, which is 9.1 times 10 to the minus 31 kilogram. So I can cancel kilograms. And if I take the square root, it's meter per second. So the units check. So let me calculate this. 4.1 times 10 to the 7 meter per second. 10 to the 7, good, wonderful, thank you. Continue. Now let's think about electric potential and electric field. And I first want to consider something like this. We have some electric field lines, and we want to go from some point A to some point B like this. And at any point, I have a displacement vector, which I call it dl with an arrow on it to show it's a vector. And we have like an electric field, right? Here, maybe it's like this, there's like that. Here, maybe electric field is like this, and the path dl is something like this. So I want to remind you the change in potential energy is delta U, UB minus UA. It's the negative of the work done by force. Since we are thinking about an electric field that changes from position to position, so we have to keep the integral form. So it's minus the integral from A to B F dot dl. And of course, I told you that we can only think about potential energy differences. So we can only talk about potential differences. So let's think about VBA defined as VB minus VA. And this is equal to, if I use this form and divide it by charge, I'm going to get minus the electric field times dl from A to B, okay? So this is VBA is equal to integral from A to B. There's like an overall minus sign E dot dl. So the nice thing about this form is the following. So if you look at the electric potential, it's like a number, it's like a scalar. But you remember electric field was a vector. So you basically take in the vector and you take another vector along your path and you take the dot product and sum over all little pieces and you get a scalar. And by now, I think we know it's easier to work with scalars than vectors because we don't have to deal with single components. So I think we'll see that will make our job much easier. So here is an example. For example, if you have a parallel plate, like the one we had exactly the same thing, and there's like a potential energy difference here. Let's call it VBA. And from potential energy difference, we can actually calculate the electric field. by using this formula, right? And we know VBA is equal to minus the integral of E. And we know E is constant here, so we can just take it out. Then it's like minus E times D. And from this, the potential energy difference tells you the electric fields. So it's basically, maybe I can pull it down a little bit. So E is equal to minus VBA divided by the distance, okay? Whatever the potential difference you apply, divide it with the distance, and you get the electric field. So here is, for example, an example from your book. If you have a parallel plate with the potential, applied potential being 50 volt, and the question is, what is electric field? You can basically put the numbers, like this is like the difference is like 5 centimeters, the voltage difference is like 50. You can put the numbers, E is equal to 50 divided by like this 5 centimeter. And if you work it out, it's like something like 10 to the 3 Newton per Coulomb. Maybe we can do a little bit more examples. Let's just think about this guy. So this is example 4 from your book. So here is a charge conducting sphere, and we would like to determine the potential at a distance r from the center of a charge conducting sphere of radius r naught. For A, r bigger than r naught. For B, r is equal to r naught. And for C, r is less than r naught. And the total charge on the sphere is Q. Okay. So let me start. So basically, we can use this formula we just introduced. VBA is equal to E dot dl, and the electric field for a charge sphere, if it's outside, it's like 1 over 4 pi so naught Q over r squared outside. What is the electric field inside? All right, exactly, thank you, 0 inside. And now we can calculate VBA is equal to minus from some A to some B. Let's put this E, thinking of outside. It's like 1 over 4 pi epsilon naught Q over r squared. And for dl, I'm thinking of a radial vector. So electric field and this dl are in the same direction. So dot product gives me something like this. And dl is going to be dr for this case. This is dr. So I can take this integral, which is 1 over 4 pi epsilon naught Q over r from A to B. I can eliminate 1 over 4 pi epsilon naught Q 1 over RB minus 1 over RA. So this is the potential energy or potential difference between B and A, right? Generally, we need to take a reference point, and the reference point is generally what? It's like, we generally say V is equal to infinity at R is equal to, V is equal to 0 at R is equal to infinity. Then this term can be 0. Then for a general V of R, the potential is going to have something like this, 1 over 4 pi epsilon naught Q over R outside. So B, we can just put R is equal to R naught on the surface. V is equal to 1 over 4 pi epsilon naught Q over R naught. And C, now we need to take VBA is equal to minus A to B E dot dl. So now we start from inside, some A inside. This is going to be minus A to R naught E dot dl minus R naught to RB E dot dl. And now we know the electric field inside is 0. So the first term is going to give you 0. And the second term is basically the same thing with this one. So V is equal to 1 over 4 pi epsilon naught Q over R naught inside, which is a constant. All right. Now we can plot this. Let's plot this and see how it changes. So let's squeeze it in here. So this is R. This is R naught. And this is V of R. At the surface, I have something like this. And then it decreases with 1 over R. And inside it is constant. And this constant is same as the surface. So we can just write something like that. Okay. We can compare this with the electric field. Let's also plot the electric field separately. So let this be electric field. So this is again R. This is again R0, something like that. But this one is electric field. So let's show it with blue. The surface we know is going to be, this is 1 over R squared. And as soon as you enter inside, electric field is 0, something like this. Okay. So let me write it a little nicely. Oops. This is 1 over R squared, whereas this is 1 over R. Maybe another example. Maybe we can calculate the potential due to a point charge. So here is a point charge, some Q, and electric field. We know the electric field of point charge. It's like what? It is 1 over 4 pi epsilon naught Q over R squared. And it's radial out for every point. And we would like to calculate the potential between A and B. Okay. So VBA is equal to VB minus VA, and this is minus A to B from A to B dl dot E. And I think I can do this again, but it's exactly the same integral. I just put this guy, take the integral, and I have something like this. And we choose V is equal to 0 at R is equal to infinity, then potential of a point charge is found to be 1 over 4 pi epsilon naught Q over R, right? If you have a point charge here, and if you are a distance R from the point charge, potential is like this. And this is generally called a Coulomb potential, right? Because it kind of comes from Coulomb's force, 1 over R squared, but in its potential form. So here is an example. So the work required to bring two positive charges close together. What minimum work must be done by an external force to bring a charge Q from a great distance away to a point 0.5 meters from a charge Q 20 microcoulomb. So here's how I would do it. So let's put a charge, and this charge is going to have some field, right? Something like this. Oops. Last one, they're all in the same direction. And the potential for this charge, we just calculated. So V is equal to 1 over 4 pi at any distance R, epsilon naught Q times R. Now I'm thinking of putting a charge, little q, some distance away. So the potential at this point is this expression, but I know how to get the work done, which is the change in potential energy from the potential, which is what? Right? Or maybe I can do this like that. Work is minus U, which is equal to Q times V, but this should be equal to 1 over 4 pi epsilon naught, Q, and the distance is R. So let's put the numbers to see how this works. So this is work is equal to K is like 8.99 times, what was it? 10 to the 19 times 3 times 10 to the minus 6 times 20 times 10 to the minus 6. Divide this whole thing with 0.5. Is that correct? Oh, sorry, 10 to the 9. Is that correct? All right. So this is what? It's equal to 1.1 times 10 to the 3 times, let's count the powers. So I have 6, 12 minus 9 is equal to minus 3. There's like plus 3 here, so this whole thing is like something like 1.1 joule. Calculate the electric potential. Okay, there's like a charge configuration. There's like a Q1 here, Q2 here. There are 2 points A and B. And our task is to calculate the electric potential at point A due to 2 charges and at point B due to two charges. Okay. So let me do this. I think maybe I can do A and you can do B. So V at A is equal to what? 1 over 4 pi epsilon naught. It's like Q1 divided by, I don't know, let's call this R1 plus 1 over 4 pi epsilon naught. Q2 divided by R2. This is equal to, okay, 8.99 times 10 to the 9 times Q1 is minus 50 times 10 to minus 6 Coulomb divided by 60 centimeters is what? 60 times 10 to the minus 2 plus 50 times 10 to minus 6 divided by 30 times 10 to the minus 2. I think I can do these numbers like what? 7.5 times 10 to the what? 10 to the minus, or 10 to the 3 volt. 10 to the 5? Okay. So this is 5. Ten to the 5, it is. All right. Charges are minus. So distance is like, this is 40, then that's also 40, right? Maybe I can write it 0. Thank you. Thanks for coming. I'll see you next week. Have a nice day.